Next up, we have Greg Bedwell from SN Systems, Sony. They have worked on the PS4 toolchain. I think it's a great example of some of their LLVM work, significant LLVM use in Europe. And you're going to talk to us about the launch and give us a little bit of a post-mortem of that launch.
Yeah.
Greg.
Okay, thank you. Yeah, so introduce myself again. So I'm Greg Bedwell from SN Systems, which is a wholly owned subsidiary of Sony Computer Entertainment. And I'm going to be talking to you today about the developer toolchain, specifically the CPU compiler for PlayStation 4. So we launched PlayStation 4 in Europe and the United States last November, and in Japan this February. And recently we announced that as of the 2nd of March this year, we'd sold 6 million PlayStation 4s worldwide, with software sales of 13.7 million. So we're pretty happy with how it's doing. The main processor is a single chip custom processor with an x86-64 AMD Jaguar CPU and a 1.84 teraflop AMD Radeon based GPU. And it's all supported by 8 gigabytes of lightning fast GDDR5 RAM. So we announced at the LLVM developer meeting in California last year that we're using Clang as the CPU compiler for PlayStation 4. And if you've not already seen that talk, then I do recommend after this going off and finding the slides in the video on llvm.org, because I'm not just going to be repeating the same content here. Instead, now that we've successfully launched PlayStation 4, I think it's a really good time for us to just take a look back at that initial period of development up until the launch of the system and just really see how it's gone for us with this new technology we've been working with and with this new community that we've been trying to be a part of. And especially when comparing it to our previous experiences with other technologies on previous systems. So I'm going to start with a really, really quick bit of history just to explain who we are and where we've come from. I'll try and rush through this. So SN Systems was founded in 1988 to provide development tools for the games industry. It was an independent company at that point. And in 1990, we launched SciQ for the 16-bit systems of the era, which included a DOS assembler and debugger and a linker, which happens to share some similarities with the Atom model used by linkers like LLD today. And in fact, the PlayStation 4 linker actually uses a lot of the core code from that original incarnation all the way back then, although significantly developed since. In 1994, Sony Computer Entertainment entered the market with PlayStation, and SN Systems partnered with them to provide SciQ as the official development environment. By this time, we were providing GCC as a compiler for that system, though heavily customized for the needs of game developers. Sony followed up the success of PlayStation with PlayStation 2 in 2000, and SN Systems provided the ProDG tool suite as one of the available options for developers. By this time, we felt we were starting to hit the limits of what we could achieve with GCC without significantly diverging from the upstream implementation. So we started investigating a proprietary compiler technology based on the EGG front end, which we called SNC. And in 2004, Sony launched PlayStation Portable, and SN Systems provided SNC as part of that ProDG suite. And then Sony Computer Entertainment acquired SN Systems in 2005 to join the technology platform group to work with the existing internal teams on the official tools. In 2006, we launched PlayStation 3. We provided both GCC and SNC as available compiler options. And generally, by now, we've seen that most teams on PlayStation 3 have switched from GCC to SNC because of the benefits it provides in terms of code size, code performance, build times over GCC. It was around this time that we started keeping an eye on LLVM as a potential future technology. And in fact, Sony Computer Entertainment's Worldwide Studios organization started actively investigating and contributing to the LLVM project. So you may know Alex. But those of us in the technology platform group concentrated on making the existing technology that we had the best we could, and the best in the industry. In 2011, we launched PlayStation Vita, and we considered LLVM as a potential compiler technology this time around, but we felt it was still not quite mature enough for the timescale that we needed, even if we put all of our effort behind it. So we went with our already proven and mature SNC compiler, but we could see the rapid pace with which LLVM was improving, and we had a new system around the corner. And SNC had only ever targeted RISC platforms, and we were going x86, which brings us to PlayStation 4. So we started development of PS4 years ago, And we made the bet that LLVM and Clang would be mature enough for our needs this time around and our timescale. This presented us with a really, really big problem, though, because PlayStation 4 was really, really secret at that point. And there was a real concern that any sudden influx of Sony contributors to the upstream project might signify that we were working on something new, especially if we started contributing changes to the x86 backend. The result of this was we had to work in isolation from the community for a really long time, implementing changes locally, and then watching with great sadness when those changes we couldn't contribute back because of the secrecy were then replicated upstream. So we did a whole bunch of work on x86 intrinsics that we just couldn't send upstream. All changed in February 2013 when PlayStation 4 was announced, and since then we've been gradually drip feeding all of our existing backlog of changes back into the upstream, and we've been doing as much of our new work as possible first. So you may have seen my colleague Andrea, for example, been doing a lot of work on DAG Combine. So we've got people, teams all around the world working on compiler technology within Sony Computer Entertainment. We've got the main SN Systems site in Bristol, where I am, includes teams working on LLVM, and we've also got the SNC team working on PlayStation Vita down there. We have an LLVM team based in San Mateo in California, which is part of Sony Computer Entertainment America. And in fact, the LLVM teams in Bristol and in San Mateo work together as a single Scrum team. So we do our best to work together as closely as possible, despite the geographical divide. And we've got a team working on SNC in Campbell in California, part of SN Systems. And we have the SCEI team in Tokyo, who primarily work on system libraries, but they do some LLVM work as well. So we've also got the aforementioned Sony Worldwide Studios organization, who are literally worldwide. So I'm going to go right back to the beginning of our LLVM development and focus on some of the earliest decisions we had to make. This is not the most glamorous of subjects, I'm well aware, but it's really, really important, we feel, to get these things right from the very beginning because it just impacts all of the workflows going forward. So as you can imagine, we already had some experience testing compilers, and we had a number of systems already in place that we wanted to make use of. So by sharing our test system between all our different platforms, then we can make sure that they all benefit. So a regression test added for PlayStation Vita for SNC should be available to Clang on PS4 and vice versa where possible. And this led to our first big decision where we already had an internal continuous integration system used by all of our other tools that we provide. So there's SNC, we have a debugger integrated directly into Visual Studio. We have performance analysis tools and a distributed build system tool to speed up builds by sending them out over the network. And we've got the philosophy that we don't just provide a bunch of independent tools, but we provide a fully integrated tool suite. And our testing is designed to reflect that where possible. So we do a lot of system level and integration testing. And we had to weigh up the pros and cons of using our internal continuous integration system versus BuildBot, as favored by the community. And we eventually came to the decision that we had to use our internal CI system for now, but we're looking at ways that we can more closely integrate with the open source BuildBot testing. And Worldwide Studios do a lot of work with the BuildBot as well. Next decision was easy. We had to build LLVM under Visual Studio on Windows. So the games industry is really, really heavily Windows-based and really heavily Visual Studio-based, just due to the platforms that are kind of predominant there. So we had to build LLVM under Visual Studio because we didn't just want to provide clang.exe to our licensees, so the PlayStation developers out there, but we wanted to also make the LLVM and the Clang tools available to them to do their own interesting projects with. And in fact, a lot of them have done some really, really cool stuff with them, which I hope will be the subject of a future talk at a future one of these conferences maybe. But it meant that we had to provide Visual Studio built libraries. So you might recognize these as the default Visual Studio configurations for the CMake version of LLVM. This didn't really suit our workflow for a few reasons. The first issue we had is that by default, unless you configure it at CMake time, the only configuration with assertions enabled was the debug one. On SNC, we'd found the pure debug configuration was just far, far too slow for any of our internal testing because we were building quite large code bases. But the enabling assertions on the release build would slow the release build down too much for our users, where build time is really important. So we needed a middle ground. So these are some build times for a game project on PlayStation 4. It was a project kindly provided to us by a development studio to help us with our testing. It's kind of small to medium-sized projects. It was about 1,500 source files, moderate use of C++, nothing too heavy. We didn't actually have this data available to us at the time, but we were able to extrapolate from smaller code bases we had when we made the decision. We're just building exactly the same configuration of the game here. We're just changing the version of Clang, or the configuration of Clang that we're building that game with. And so as you can see, the debug configuration is essentially unusable. It's kind of over 2.5 hours just for a complete rebuild of that game that we want to test with on every check-in. But the release plus asserts configuration provides a really nice middle ground, but it's got too much of an overhead over that pure release build for us to consider just globally enabling assertions in CMake for all configurations. As I say, just the build time to our licensees is really important. So we went with the same set of configurations that we did with SNC, with our CI testing using a mixture of checking, aka release plus asserts, and pure release, just to make sure we had some coverage on what we were actually shipping. And I'm actually keen to add a fourth configuration to this, because, which is debug plus optimized table gen, because most of the time I'm not debugging table gen, but that debug version of table gen subsequently gets used in the build and is so slow to build it just really bottlenecks the entire build. There's actually one more difference between this and the SNC configurations, which is debug info on the optimized builds. So, well, I did this experiment. Here's a 64-bit Clang build under Visual Studio, about 37 meg in size. And we know that Visual Studio, which we're building with, stores the debug data in separate PDBs. So in theory, we can enable debug data without affecting the executable in any way. So enable PDB generation, and it got bigger. So that was wrong. But I went back and looked at our SNC configurations and saw there was one more flag that we had enabled there, which is dead stripping on Visual Studio, which isn't actually enabled on the upstream version of LLVM or Clang at the moment. Enabled that, and the executable shrunk from 37 down to, or indeed kind of over 40, down to 30, almost exactly 30 meg. So massive saving. But the question everybody's going to be asking now is, well, what if I keep the dead stripping and lose the debug data? Well, actually, exactly the same executable. So we were happy with that. So we enabled debug information in all of our builds. Yeah, there's one more change we made. So if you do Windows development, you'll know how awesome this little box that pops up is for any sort of automated build you want to do. And we didn't want to have to ask all of our licensees to use the Kill the Doctor tool on all of their builds. So we added a modification to Clang so that that box would be suppressed in the checking and release builds. We kept it in the debug builds because occasionally when debugging you might want to do kind of a post-crash attached to a process. So by this point, we had our test systems in place, and we ported as many of our tests as we reasonably could from other platforms. But there were still big holes in our testing, especially in performance testing. We know a few things already. First of all, the Clang and LLVM regression suite that's there is really good. So it's not like we felt we were missing any sort of coverage whatsoever, but how much coverage is too much coverage? Another thing we know is that game code's really big. I mean, it can be really, really big. Thousands of files and millions of lines of code, or tens of millions of lines of code. We know from extensive performance analysis on our previous platforms that a lot of that code is actually really quite cold code, not executed very often, but the hot code is really, really hot and absolutely critical to performance. And we also know, because we were right at the beginning of developing PlayStation 4, there really wasn't any PlayStation 4 software out there that was big enough to show that sort of performance characteristics. We didn't have any sort of runnable code bases. We could have ported games over as build tests, but actually to get them running on a whole new architecture with the timescale and resource we had available, it just was out of the question. And this has had really, really big implication on measuring performance, because we found that those large code bases have completely different performance characteristics to the small benchmarks and micro benchmarks we had available. And again, on previous platforms, we found that in the worst case, optimizing for benchmarks actively harms the performance of large-scale code. Whereas the biggest wins that we've had in real-world game code have come from cold code optimizations, which just don't show up in benchmarks. So it kind of means that any sort of reliable performance testing was just really hard to do early on. But thankfully, we also know that correctness is just by far the #1 priority. especially early on when everybody is bringing up their code bases on the systems. So we chose to focus on correctness testing early on and then just bring up the performance testing infrastructure as we started to get examples of real-world code bases. As I said, the existing testing is good, but there are a few notable holes that we found. The most important one to us is the usage of SIMD language extensions, so all the X vector type stuff, and also things like the intrinsics. So we wanted to write some tests for that. We're software engineers, so we all know the old saying, if you write a test, you've got a test. If you teach a man to fish, you've got tests for life and fish. So actually, we already taught that man to fish on PS3 and PS Vita because we faced exactly the same problem there. We had the UltiVec language extensions that we needed. We didn't have test coverage for on PS3. Neon intrinsics we didn't have coverage for on PS Vita. So we wrote a random test code generator. It's not a new approach at all. LLVM's got the LLVM stress tool for generating random IR. And there are tools out there like CSmith to generate random C files, but none of those existing tools that we found quite matched our problem domain. What we wanted was to generate random C++ code that would exercise all parts of the compiler from just the front-end support through to the code generation optimizer and even debug info, so we could actually run these things in our debugger and make sure that it looked reasonable. So simplest kind of random test can be modeled to look a bit like this. You just pick a random operation, you stick some random input into it, and then you just check the output that comes out. Actually, things like loads and stores don't quite fit this model, but I'm going to ignore those just for the sake of brevity. So we pump some random input, look at the result, and then you can easily build it up just by finding another type where the output matches the input type of your original one, stitch them together, kind of join them up, and eventually it's really easy to just generate huge test programs. So the other day I generated, I think it was a 48 gigabyte C++ file full of vector operations. It's a bit sadistic, Clang didn't like it, but I wouldn't expect it to. Of course, as I've described it right now, it's just a big constant folding test. So we can fix this just with a liberal sprinkling of the volatile keyword, and we can move sections of that generated tree out into no inline functions, and then we can even model them as operations in their own right with inputs and outputs to feed in. And we probably want some more interesting control flow, so just put huge sections of that into conditionals, into loops, and with this, this approach, catching compile time errors is easy, even trivial. So I tried it on top of tree a couple of weeks back and managed to find a previously uncaught compiler assertion within the first 15 seconds of testing. So there's real value to this approach, and I've raised it on Bugzilla. I think it's been subsequently fixed now. Runtime errors are harder. So first of all, you need some sort of reference to compare against. So on PS3, we compared GCC against SNC, and we found bugs in both compilers just by looking at the places that they were different. For PS4, we've only got Clang. So what we generally do is we compare the O0 results to the O2 results. Of course, this relies on the assumption that all the behavior is defined to be the same at all optimization levels, which is clearly not the case at all. So you work around that by providing just a safe wrapper around that undefined behavior. So if you've got, say, a cast to increase the size of a vector type to a larger one, and that leaves undefined bits, just make sure that that wrapper masks off all of the undefined bits, so that they're defined for the purposes of the test. So this is where we really started needing to be able to reduce runtime optimization bugs in order to work on them. And LLVM has a solution already for that called BugPoint, and we've had some success with it, but we've encountered some issues. So first impressions, I'd say, count for quite a lot. And my first impression of BugPoint is it needs a little bit of love, and it hasn't been overly tended to in recent years. First of all, it doesn't really seem very happy on Windows. It works most of the time, but it kind of has an odd habit. I've still not quite figured out why. It complains about a lack of my GCC installation on Windows when I'm not doing anything that involves GCC at all, as far as I can tell. It might just be down to a documentation or probably just user error, but it didn't seem particularly friendly. And the next point is a bit controversial, so please hold back on the rotting fruit. Let me explain my case. And that's integration directly with Clang, because I know BugPoint is a standalone tool, but it's something that would be really, really useful for our use case. And let me explain why and how we solved this problem with SNC, or what our problem is and how we solved it. So as I mentioned, we make use of a lot of game code kindly donated to us by game studios around the world for our CI testing. So here's my game. or I should say it's my terrible program art representation of a game. This is actually what a game looks like. This is Killzone Shadowfall by Guerrilla Games. It was a launch title for PlayStation 4, and Guerrilla Games are part of the Worldwide Studios organization. But you're going to have to use your imaginations, because I'm not as good an artist. So this is what a game should look like. And then we implement a new optimization somewhere locally, and then we try running our game with it. All of our test suites have passed, but we run the game and this happens. All the colors have messed up. It's absolutely the worst kind of bug to track down, because we don't have a nice crash to give us a call stack to work back from. We don't have any sort of change in TTY output to kind of give us a clue on what might have changed. It's just the colors on the screen are different. Everything else is working perfectly. Essentially, we've got no idea where to look. We just know that somewhere in our tens of millions of lines of C++ code over many, many files, something somewhere is miscompiled. And these are all kind of real examples of the sort of things we've seen. This was a bit freaky. All the characters' faces are upside down, the geometry going weird, everything going wrong at once, but still no clues as to what's gone wrong. So when we wrote the new SNC optimizer for PlayStation 3, we kind of considered this problem and we factored a solution into the design. So basically, an optimization in SNC looks a bit like this. So you kind of check whether you can perform an optimization, and then also the final check is you call this opt-enabled function. And then we maintain an internal counter of the number of transformations performed. So in the transformation, that's even if we're doing the same optimization twice, that counter would be incremented twice. And then if we do another optimization, it's incremented further. So we keep that internal counter, and then there's a command line argument that you can specify to just put an arbitrary threshold onto the number of transformations performed. And the opt-enabled function basically checks whether that threshold's been exceeded. And then the trace op function, among other things, just increments that counter. And so this way you can easily just tell the optimizer to stop doing any further work at any arbitrary point. So we use a harness called AutoChop. It sits on top of the game build, which might be one of 10 different systems. There's no standardization on that sort of thing. But it automates a lot of the process for us. So here's my game. We pretend it's only 8 files long, with each of those red boxes being a source file in the game. We build it fully optimized, and we observe that the game's broken. Build it unoptimized, and we observe it's OK. And then from there, we can just binary chop until we get to this point where this file makes the difference. And this is where the maxops idea comes in. So we build with some arbitrary threshold, and then we just binary chop again. I'll skip out a few steps. And we get to this point where with 988, say it's OK. We increase to 989, and it's broken. And then it's just a case, we can look at the compiler trace to see exactly what happens. So there's some sort of permute optimization going on there. And then just diffing the IR before and after. In almost all cases, it comes down to 1, maybe 2 lines of difference in IR. And you can usually spot the bug just from looking at that without any further investigation, which is pretty useful considering kind of just before we started off with millions and millions of lines of nasty C++ code that we just didn't know where to even start. So I've got a question for everybody, and I'd be really interested afterwards to hear people's thoughts, is could we implement something similar to this in LLVM and Clang, or could we make bug point actually work for our use case here? As I say, I may just be using bug point wrong. It's kind of hard to figure out from scratch exactly how to do it, but the key thing is we need to be able to do it from any arbitrary build system which has Clang built in. So, okay, back to the retrospective. So by this point, we had our internal systems in place, and we were ready to release to our licensees, except for not, because actually, as part of the PS4 SDK, we have to do all these other things. And first and foremost is produce documentation. And I'm afraid this is one area where LLVM doesn't do so well on. Quite often, the answer just seems to be look at the GCC docs. It's probably about the same. The other thing is release notes. Now, I'm slightly unfair on this point, because this has been a lot better recently, but we found that a lot of times release notes were aimed more at internal developers than kind of end users of the compiler. And the main issue with release notes we have comes down to Clang diagnostics. Because we've seen the trend, which we totally are on board with. It's a great thing that Clang is getting more and more strict with every release. New diagnostics, new warnings, new errors. But as part of our release note process, we have to document every single change, whether that's a new diagnostic that's been added or just an existing diagnostic has been made slightly tweaked to be more strict. And the way we've solved that is we just have to build every line of code we have available to us and just check to see whether there have been any changes in the diagnostics, then reduce those down to small examples. This didn't used to produce it, now it does, and here's the change you can make, and we include those in our release notes. So it'd be really good if we could work with the community to figure out a way to actually kind of include that sort of change into the release notes as those changes get made. But we don't just want to sit back and complain. We've had to write all of this comprehensive documentation for the PlayStation 4 SDK, and there's no point keeping it private, so we want to donate it back to the community. Starting with our x86 CPU intrinsics guide. There's some previous discussion on the lists about that, so please stay tuned. Hopefully you'll be seeing that soon. There's one more absolutely huge consideration. It's really important to us, which is forward compatibility of the ABI. Keeping a stable and fully compatible ABI is absolutely essential to us, because PlayStation 4 is going to be around for a long time to come, and we want to be continually providing our licensees with the latest and greatest version of Clang. And as I said, there are already millions of Blu-ray discs and downloads in people's living rooms across the world. They've all been built with Clang 3 something, and dynamically linking against system libraries built with that same version. But as we start to get newer versions of Clang, those libraries are going to get updated, and the games that come out in future will be releasing with that version, and it's going to kind of continue. So hypothetically, in 10 years' time, when we're all using Clang 13.2 or 4 or whatever, and the system software will be built with that version, but all those games built all the way back in 2013, 2014, still need to dynamically link correctly with them, and all the versions in between. So this is the most important rule that we have to follow. For us, any change whatsoever in the system ABI at any point is just the worst kind of bug imaginable, worse than miscompiles or anything, because it has the potential to affect already shipped code. And unfortunately, that includes maintaining existing ABI bugs at the point where we lock the ABI down. We've already had to diverge from the upstream implementation in places where we found ABI bugs have been fixed since that version. It wasn't a problem with S&C because we fully owned and controlled the code base, but we need a better solution this time around. So we've put a huge amount of effort into writing a full C++ IA64 ABI test suite designed to work with both S&C and Clang and exercise kind of every single corner of the spec. And we've been doing a lot of code coverage to make sure it's exercising all of the different bits of the front ends. And we really would like to contribute it upstream as well. We're still investigating the possibility just to make sure that we're able to do that. So please stay tuned, again, for further updates on that, but hopefully. And I feel like this wouldn't be a full kind of post-mortem if I didn't at least touch upon the reaction from our licensees to the PlayStation 4 toolchain. But my colleague Paul already covered this pretty well at the November DevCon. There's not really much more to say, but the spoiler is like it's just been the most well-received toolchain that we've ever provided, so that's fantastic. But I'm going to just kind of touch upon one thing that Paul did already cover. It's everybody's favourite subject. S&C supports this, GCC does, Microsoft Visual C supports it, Clang doesn't. And the reason that we just bang on about this so much and probably irritate everybody is because it's just so important to all of our licensees. So we put a load of effort into making sure that we're constantly communicating with them. We'll go visit them at their studios. We've got our dedicated developer services team whose job it is to provide support and to ensure that all that feedback makes it to us. And it's important to us that our licensees can always communicate directly with the people who actually are writing the tools rather than having to navigate multiple levels of support. So I've been out to many game studios, talked to them just about how they're finding the compiler, and this is the one feature request that I've heard, and we all hear every single time, pretty much without exception. And talking to them, this is the main use case. So games typically run at full hardware utilization. They've got no performance overhead to spare whatsoever. They have to run fully optimized. And running anything less than full optimization basically harms performance to the point where the game becomes unplayable and therefore it's unusable for reproducing bugs. So often you might have to play the game for a little bit in order to actually get to the point of a bug report that's landed on your desk. So for this reason, they do all the debugging at full optimization. And if anybody's tried doing full optimized debugging with Clang, it's not great. And there are plenty of ways to attack this. So we really want to put a lot of effort into actually just improving the optimized debugging experience, because that will improve the situation. But it is a huge task, and still we'll probably never get it to be as good as that O0 debugging experience. In S&C, we had some level of success with kind of an optimized but debuggable level of optimization, where we traded a small amount of performance for a big increase in debuggability. But even sometimes then, that small amount of performance was just too much. What they're used to doing on other platforms is this. The idea is you just turn off optimization on the kind of minimum number of functions possible so that they can debug them as if it were an unoptimized build, but without the trade-off of disabling optimization on the entire file. Especially as you may have heard yesterday, a common trick in the games industry is the Unity build of files where you just hash include it all into one or a few kind of Uber files. So in theory, disabling optimization on just one file is basically disabling optimization on a quarter of your entire project. We put a proposal onto the lists pretty soon after PlayStation 4 was announced for this. It didn't really get much feedback to suggest it was a feature that would be accepted. So instead, we were advised to try contributing a smaller and less intrusive feature. So we've spent a while pushing to get attribute opnone accepted, and finally we upstreamed it maybe a week or two ago, so thank you. That's really great. And the reaction from our licensees has been positive to mixed. It's definitely seen as a step in the right direction, and it is useful, but it can be a pain for them when they want to disable optimization on more than kind of a dozen functions at a time, or say disable optimization on a whole class. And it turns out that one of the reasons the range-based solution is so requested is because so many of our licensees actually just abstract it away to kind of a compiler-independent interface, just using on and off macros. And the opnone attribute model just doesn't fit this, and means that Clang is the odd one out. So we need to think of some way to satisfy the requirement. We'll probably continue to push for kind of a ranged-based opnone solution. So really, that's a really brief summary of the last few years. There's so much stuff that I wasn't able to cram into half an hour. But kind of I hope it's given just a decent flavour of some of kind of our main experiences with this technology, which overall have been really, really great. So I want to say thank you to everybody in the community for just making this what I honestly believe is it's the best compiler technology out there, bar none. It's not perfect in all respects. There is still work to be done. We all know that. But I hope that we'll be able to contribute our ideas based on our experiences. And I want to say it's been really inspiring to just be here and just hear all of the ways that it's just getting better. So the message is you're going to be seeing a lot more of us. We're going to be working alongside you for a long time to come. So thank you very much. And I'll be happy to take any questions.
All right, let's thank our speaker.
Thanks for the great talk. You mentioned you want to open source the test suite. What about the test generator, please?
So yeah, the test generator, for sure. I didn't mention that one specifically because I haven't actually discussed that one with our management, so I have to be careful what I say. What I've been doing at the moment is just running it on the upstream compiler periodically, and I'll continue to do that and file bugs where necessary. So we'll kind of gradually build up, just through the added regression test, kind of more test coverage on that. The test generator it's an interesting one because it is totally cross-platform, and it has got a few hacks in it where there's kind of some manual processes involved. But I'm sure we could do some really interesting things to actually make table gen, say, directly produce some of the some of the inputs that requires. That currently I just have to massage files manually into it. But I mean, I'd be really happy to talk to anybody about either upstreaming our existing one or maybe kind of implementing something new that's a bit more directly suited. But it's a really powerful technique, so I really do recommend making more use of it.
So more of a comment than a question. Bug point is really, really old, and so the GCC part I think is just historical and no one has cleaned it. And it's been on the list to rewrite it, I think, for like 5 years or so. So if you guys want to rewrite it, by all means. The main idea is don't make something that's attached to LVM, just run the different passes. But one thing that's nice on the way it works, as opposed to what I described, like since it reduces both the test case and the passes that run over it, once it's done, you pretty much have a test case to check in.
Right.
And if you're reducing like the full program and just reducing the number of passes, then okay, I found a bug, now I have to go write a test case. And the one other, sorry, what was the yeah, no, those are like the main issues of bug bounties. So if you guys want to rewrite it, it would be certainly very welcome.
Okay,
to
I'll definitely have some conversations with some people just about what can be done in that area, because it's an important area to us, as I kind of described, and there's no point in coming up with something that just satisfies our use case and not the rest of the community. So yeah, it'd be good.
One question, you mentioned the benefits you're seeing with Clang and LLVM in the areas of build time and the warnings and so forth. What about the performance of the generated code? Are you satisfied with that? Have you seen issues with that? Have you compared it against anything else?
On the whole, performance has been pretty good. It's definitely not perfect in terms of generated code. And so you can see kind of a lot of the changes that we've been upstreaming, especially in places like DAG Combiner, to do that. I mean, but it is good. I guess what's going to happen is because the first year titles on the PlayStation platform are generally not going to be pushing performance as hard as future kind of generations of titles. So we'll probably start to get more feedback from our licensees on code gen later on, because there's a lot of really low-level guys there. They will be looking really, really closely at all of the code gen. So if there's an extra move instruction where there shouldn't be, we'll hear about it straight away. So they'll file bug reports about that sort of thing. So on the whole, it's been good. There are improvements to be made, but as I say, it's kind of my general message. We want to work with you to make those.
Do you share source code for the toolchain with your licensees?
I don't believe so at the moment, but we do provide headers and libraries.
Any more questions?
So how often do you merge upstream LLVM into the product?
Okay, so this is... So if I'd had kind of an extra 10 minutes, this would have been the next subject in there. Merging has been the source of so much pain for us. We've been doing it wrong, and we're going to be doing it better. So generally, we've been doing merges kind of every couple of months, maybe even longer than that. And what we found is because it seems that the rate of change to the upstream is kind of increasing each time. Like the length of time it takes to do that merge is increasing each time, and we're kind of getting to the point where it almost would take longer to do the merging. It would take kind of more than 2 months to merge 2 months worth of changes. So we're looking at a system at the moment where we kind of do daily or even per check-in automatic merging, then we only have to get involved in that process when there are conflicts.
Okay. Anyone else? All right. Well, thank you again, Craig.
Okay, thank you.